In this video, we present a case study and findings from a project on digital twin in discrete manufacturing. The project is conducted at Tampere University and is a part of TECHBOOST, a Finnish initiative that helps SMEs adopt new technologies in robotics and AI. The case study is developed at RoboLab, Tampere University, together with TECHBOOST industrial partner Dynaset. It focuses on a robotics workcell with three main components: a FANUC collaborative robot, a Cleco wireless nutrunner, and a height-adjustable manual assembly table. Each of these have a virtual replica in a 3D environment. Changes in the physical or virtual world are reflected in real time in the other, so the setup is a real digital twin. Digital twin can mean slightly different things depending on the sector and definition used. But in manufacturing, the idea is simple. A physical asset, its virtual replica, and a two-way data connection between them. This concept, first described in the early 2000s, is still the foundation of how digital twin is understood today, and it aligns with international standards. Put simply, a digital twin is a digital mirror of your system, continuously updated so that actions in the real world and virtual world match each other. The motivation of this case study is to demonstrate how a true bi-directional digital twin can be created, even when combining modern devices with the older legacy hardware. For many SMEs, this is a common challenge. You may already have machines that are productive, but they are not designed to connect easily to modern digital systems. By solving this gap in a practical case, the project shows how digital twin can be applied cost-effectively, even without replacing existing equipment. In our setup, the robot and the nutrunner already support modern industrial connection. They can exchange information with the software directly, making the twinning straightforward. The assembly table, however, only accepts basic control signals and has no way to send back data. To bridge this gap, a small relay board is connected to the table's LINAK controller. This low-cost IoT device communicates with visual component software via OPC UA and MQTT protocols. A simple laser sensor measures the table height and sends feedback back into the system. This creates a complete two-way link. The 3D model and the physical table are always synchronized. At the same time, the system uses Node-RED to provide a simple dashboard for direct control of the table, which is useful for commissioning or operator types without needing the full 3D environment. Here's a quick look at the integration diagram. Feel free to pause the video if you would like a closer look. The project reaches three main outcomes. First, it achieves true bi-directional control between the real and the virtual system in discrete manufacturing context. This is considered a major step in digital twin development. Second, it shows that legacy devices can be integrated using affordable components such as MQTT and IoT controllers. For SMEs, this proves that you don't need to replace older machines to benefit from a digital twin, but may be able to do this with cost-effective sensors and microcontrollers. Third, the setup managed to run continuous twinning at sub-second latency. This level of performance is demanding, but important when aiming for real-time synchronization. In addition, two side results are achieved. The table can be operated through Node-RED without the 3D model, suggesting a path to low-cost lite MES solution. And the setup is successfully live-streamed, opening a possibility for remote monitoring and teleoperation. To summarize, this case study shows how digital twin can be built step by step, even when mixing modern robots with legacy devices. For SMEs, it highlights that digital twin is not only for large corporations. It can be achieved in a practical and cost-effective way. Thank you for watching, and we invite you to think about how a digital twin could be applied in your own operations.